Okay, we're going to try GES1, the General Engineering Science 1. We're going to do March 2018, and we're going to run through these one by one, nice and slow. You know, you guys can hold your attention a bit longer than the average YouTube viewer, so this should be fine. Okay, let's look at number 1. It's required to cast a sphere and a cube by melting aluminium rod stock. Let's see, a cube and a sphere and a cube. That's I can't understand all that information in one go, so I'm not going to read it anymore. I'm going to read the whole question just slowly. I'm just going to take these out to start with. So we've got a sphere and we've got a cube. There we go. It's quite difficult to understand a lot of information all at once, so I'll just break it down to little stages. So here's my cube. That should be fine. Whoopa. Okay, that should be fine. And then it tells me more information. It says the melting aluminium rod stock of 50 millimeter diameter. Oh, a rod stock. So it isn't a rod, that's gonna be a tube, like a cylinder like this guy. And I know that it's, let's put some information on here. It says that the diameter of the rod is 50 mil. Something like that. That's the same as 5 centimeters, so I could actually turn it into 5 centimeters. Seeing as everything else is in centimeters, we might as well do that. It was 5 centimeters. Now the cube, I don't know. But then the diameter of the sphere, oh yeah, that's really useful. So the diameter of sphere is going to be 5 centimeters. And the cube is to have an equal mass to the sphere. So what's going to happen is, because these are both made from the same material, they're effectively going to have the same volume. So I don't know anything about the cube, but I don't need it. I just need to times this one by 2, and then that will give me the cube as well. So that's really useful. Okay, great. So then let's have a look. I've got the sphere. Oh, I need some formulas for volumes of spheres. Let me write that up here. A volume of a sphere, you need to know this one, is 4 over 3 pi r cubed. In order to use that, I need to know what r is. So let me go get radius of this thing. It's going to be 2.5 centimeters. And that's all I need. We can just plug it in. Let's go for it. Let's calculate that. So it'll be 4 over 3 pi r cubed. My r is 2.5. Cube it. Not square it, cube it, and we can calculate that. Let me grab my calculator and we'll plug it in. 2.5 cubed, and then times that by pi, times that by 4. I'll do it slower, my bad. Times that by pi, times it by 4, and divide it by 3. That's 65. That's meant to be slower. 65.44 centimeters cubed, or thereabouts. It's a little bit more. I didn't round it properly actually, but it's good enough to show me I'm on the right kind of direction. Then I'm going to times it by 2, because remember we said that the cube and the sphere are the same. So let's multiply that by 2, and this will be my total volume. My total volume is 130. So let's write down total volume is 130.8996. 8996. There's a few more numbers, but I'm not going to take them out my calculator. I'll just leave them in there. It's fine, because we've got the total volume. Now we need to use, this will be centimeters cubed. Now we're going to use this volume to work out the length of the height of the tube, of the cylinder that we need in order to cut this bit off. So the volume of a cylinder is base times by height. That's basically it. In this case, the base is this bit. This is a cross-sectional area, if you like, which is a circle. So it's pi r squared, and the height is along it. So we'll call it like this. This is the volume of this thing. So we can go ahead and use this here. This will be for the stock. This will be for the cylinder. We finished with the cube and the sphere, actually. So let's look at the cylinder. It's going to be the volume. It's going to be pi r squared h. And we know this whole thing is equal to 130.8996. Actually, we already know r as well. We can find radius of this thing is equal to, well, 2.5 centimeters, because it's right there, isn't it? So pi 2.5 squared h is equal to 130.8996. Now we're going to find the value of h. And the good news is we can just take all of this and divide through by it. So there we got h is equal to 130.8996, that 9's a bit wobbly, over this guy, which is pi 2.5 squared. And we'll just type it in and see if it works. I've already got the number in my calculator, so I'm going to put it in brackets to make sure. Put the pi, I'm dividing by pi times by 2.5 squared. Close those brackets, it should be fine. I got 20 over 30, which is 6.666. So the height is equal to 6.6667, I suppose, but I have to put a 7 on there somewhere, centimeters. That should be the length of the tube. And it looks about right. It's not too big. It's not too crazy big. Okay, question 2 then. Let's see what we can do with this. I've got some fractions. These are really, really common in GES1 right now. So the first one is, this is number 1, A. We'll just call it A. It's x, what is that? X squared? That's an x cubed. Let me just write the question down. It's not very clear. It's x cubed over x squared multiplied by x to the 4 over 4y. Okay, that's cool. Now we got that written down nice and clear. Let's see what we can do with it. Well, I mean, we could multiply this stuff straight away, or we could simplify it. These guys are going to simplify a whole bunch. We got a couple of different ways we can do this. It depends on which way you feel better doing it. You could multiply the tops. Remember, when you multiply the bases, you add the powers. So this is going to be 3 plus 4 is equal to 7. And then the bottom bit is just going to be 4yx to the 2. That's great. And then the 7 and the 2, they can actually cancel. They can be subtracted from each other. I can explain what that is. I mean, this is really like, you talk about the 7 x's all multiplied together like this. 1, 2, 3, 4, 5, 6, and 7. And then, whoops, and then on the bottom here, we got a 4, a y, and we got 2 x's multiplied together. Now, anytime you see an x on the top, you can just cancel it out with an x on the bottom. So it's like this. Of course, writing all that out is quite long. We don't actually have to go to that detail. We can just say 7 minus 2 is 5, so x to the 5. You can see it's 5 because 1, 2, 3, 4, 5 of them. On the bottom, we got 4y. That's it. That's the first one done. Oh, no, it's not. It says make x the subject of the expression. So I'm not done yet. I've actually only got y is equal to x to the 5 over 4y. I want to make this x is equal to something. So I got to pull out x from there. What can I do to this? Let's have a look. I'm going to have to move down for a bit more space. I can multiply both sides by this 4y. Let's do that. It's going to look like this. 4y. 4y. This will cancel out. Y times y is y squared. So I'm going to have 4y squared is equal to x to the power of 5. And then to undo that, to get x by itself, I'm going to do a 5th root of both sides. It's going to look a bit like this. 5th root and 5th root. Again, that's going to cancel out. That's why we did it. Now I've got x is equal to, I'm going to flip it around so it goes the other way just so it looks better. Don't have to. That's the final answer. X is equal to the 5th root of this thing. Let's put a box around it for the final answer. So that was part A. Let's have a look at part B. Ooh, it's quite a chunky one as well. Let's make some more space for part B, shall we? Okay, so part B is gonna be this guy. It's quite a long bit of work as well. So we've got y, we're doing B right now, is equal to x squared times by z to the 3 over z squared or z squared divided by x to the 3 y z. I don't need the multiplication signs in there. Those really just make it more confusing. We're going to divide it by x squared. Okay, so what we're going to do is we're going to flip this because you want to turn a divide into a multiplication sign. And we're going to use KFC to do that. We're going to use keep, flip, change. Keep, flip, change, right? Which means we're going to keep the first one the same, exactly the same. We can just write it as being, oh, actually, well, let's keep it exactly the same. I could simplify it. I should simplify it, but let's just keep it the same for now. All right, and then we're going to flip the second one. So the second one goes x squared on top, and then all this stuff on the bottom, y, z. And then the change is you're going to change the division into a multiplication. Right, we did it. That's good. When you see a multiplication like that, you can literally just squeeze the tops together and the bottoms together. They're just all going to multiply together. So let's do it this way. This is not the only way to do it. There's lots of different ways to do it. The x squared and the x squared can actually be added together to make x to the 4. So here's x to the 4. Z to the 3 can stay the same. And on the bottom, we got z2, and this is z to the 1. So they, again, can be combined to make z to the 3. The x to the 3 is just there, and the y is just there. Now, anytime you see a number on top, that's the same as a number on the bottom. Like these z's, these z's, they can be cancelled out. Now we can do the same thing for the x to the 4. There's 4 of them on top, there's 3 of them on the bottom. We did it last time, we just did 4 minus 3. So we can do that. We're going to get x to the 1 on top over y. Okay, we're almost there, but remember the question's a bit weird. It says make x the subject. I don't normally say that, but that means that y is equal to all this stuff. Let's just make sure I didn't make any crazy mistakes anywhere. Nah, it's all good. Alright, it's just a bit different from how I remember. Y is equal to x over y. Well, I got this one from here and this one from here, put them all together. Now I multiply both sides by y, so we get y squared is equal to x. That would be my final answer. Are we good? That's it. Next question. Okay, we're going to do part 3. Question 3, let's have a go. A right cone has a sloping side of this much. Okay, let's draw a right cone first of all, because I don't know what one of those things are. I do know, but I don't want to read the whole question because it's too much information. So here is a right cone. It's called a right cone because it's made using a right angle at the center. If I draw a center on a bit like that, I suppose, it should have a right angle right about here. Rather than being like a sheared cone, which would look like something like this, which we never have to deal with, but like, you know, they do exist. Okay, so a right cone has a sloping side of 340. This is 340 millimeters. This is the sloping side, this bit here. And a perpendicular height of 300. So the straight up bit in the middle is going to be 300 millimeters. Okay, we got all that information. That's great. Now we're going to find the volume of the cone in meters cubed. We've got to be really careful because this thing is in centimeters, this thing is in millimeters, and I want to draw it in meters straight away. If we're working in meters, I want to do all my calculations in meters, please. Now you remember that, you know, 1 meter is equal to like 1,000 millimeters, so we can divide this by 1,000 to get it into meters. So this will be equal to 0.34 meters, I think, and this will be equal to 0.3 meters. Right, I need one more thing for the cone, which is the radius. But let's have a look at the formulas. The formula for the volume of a cone is 1/3 base times by the height. This is true for cones, but also pyramids, and there's also, yeah, pyramids or cones. Cones are pyramids. They just have a circular base. Anything that involves a circle seems to have a special name to it, but like this will work for square-based pyramids, triangular-based pyramids, anything we like. So the only thing we're going to do is swap out the base. In this one, the base is a circle, so we're going to use 1/3 of pi r squared times by height. That's great, but the problem is we don't have r. This is r right here. We need to solve a little triangle to get that. So let's do that right now. You can see this triangle here. It's a right angle triangle. I'll draw it off to the side. It's a little bit big. Let's make it, oh, it's still big, whatever. Here's a right angle triangle. This thing is going to be 0.34 or 340 millimeters on the hypotenuse on the slopey side, and then it's going to be 0.3 on the straight up bit, but we want the base. So how do we do the base? Is we use Pythagoras. We can use a squared plus b squared is equal to c squared, where this side could be a and this side could be b and this side could be c. We don't actually know b, but we can still plug the values in. Let's go for it. 0.3 squared plus, well, let's just call it x or something. We could call it r, couldn't we? Is equal to r squared plus 0.34 squared. Okay, I need to rearrange this a little bit so that I can get the r by itself. So I'm going to transpose it. I'm going to minus this 0.3 from both sides. So I'm going to have r squared is equal to 0.34 squared minus 0.3 squared. We do this a lot. So if you're not comfortable with it, well, we got to practice a bit more until you are comfortable with it. And then we're going to square root all that to find the r squared, or to find the r by itself. Unless, actually I need r squared, so I could leave it like that. But let's just get a calculator first of all. 0.34 squared minus 0.3 squared, that gives me, well, this number as a decimal, 0.0256, so r squared is equal to 0.0256, and I just want one r, so I'm going to square root it. So let's square root that to get just the r by itself. I'm going to get 0.16, 0.16 meters. Is that right? Well, strange as it is, looks right. Okay, great. That's my radius then. My radius is 160 millimeters, which kind of makes sense. I mean, okay, great. So now I can calculate the volume. Volume is going to be equal to 1/3 pi 0.16 squared times by the height, which is 0.3. Let's just do it all a bit slower on the calculator. 0.16. I'm going to start with the brackets because of PEMDAS or because of BODMAS. We got to do the square bit first. So that's that done. I might as well times it by 0.3 and hit equals. Times it by pi, hit equals, and then I'll divide it by 3 because this means divide by 3. Or I could times it by 1/3 if I want. Same thing. I get this number. That's actually a okay number. I could write it and I could try to convert it back into a regular number or just write it like that. And that's just okay. 8.04. It's 8.04 2477. 2477 meters cubed. Whoops, I meant 10 times 10 to the negative 3 meters cubed. That is the volume of this small cylinder, small cone in meters cubed. It does not fill up a whole meter cube. If I wanted to write it like in regular numbers, it would look like this. But standard notation is absolutely fine. This is good. This one's good. They're both good, actually. You still got the points for it. That's it. Now we got to do the next one, the angle of the sloping side. So let's make a bit more space. Let's drag it over here. The angle of the sloping side. Looks like I'm going to still need my diagram. So let me just grab my diagram real quick. Here it is. I know the base of this thing now, so I guess I could write that down as well. The angle of the sloping side. So how are we going to angle it? Like this one? Or I guess so. Or it could be this angle up here. I really don't know. How would you measure it? I suppose I'd measure it from the base. It doesn't say. Either way, even if you get one angle, you know the other, so it's pretty easy. I can write down both angles just in case because the wording is not very clear. The angle of the sloping side. So you can see I'm going to pull out that red triangle from there. Let me just do that over here. Let's pull out that red triangle. It's kind of like the same setup we had a second ago. I think it was 0.16 on the base. And I can use anything I like. I might as well use 0.3. I don't even have to use my 0.16. I could use the 340, the 0.34 they gave me for the hypotenuse. And we could work out this angle right here. No problem. We're going to write down SOHCAHTOA to do that. Let me just get SOHCAHTOA. Bit of trigonometry. So silly old Harry caught a lot of haddock trawling off Africa. Great, okay. And because, I'm going to go from this angle down here, I draw a little guy there. This is opposite him. This is the hypotenuse because it's always opposite the right angle, it's longer side. And this is the adjacent, which is next to him. So what are we going to use? I can use anything I like, basically. I'm going to use opposite and hypotenuse because this way I avoid my own calculations, which means if I made a mistake here, it won't follow through. So it'll be okay. So opposite and hypotenuse, opposite and hypotenuse. So I'm going to write down the rule for sine, which is sine of the angle is equal to opposite over hypotenuse, like that. And then I start plugging stuff in. I don't know what the angle is, but I do know the opposite is equal to, I need a bit more space. I know the opposite is equal to 0.3 and the hypotenuse is 0.34. Now, if I want to get the angle by itself, I have to apply sine -1 to both sides. So I'm going to do that. I'm going to squeeze it in here. Let's pick up that color again. So we're going to get sine -1 of both sides. What that actually does is the sine cancels out the other sign. The sine -1 cancels out the other sign. And we're just left with the angle by itself. So now I got the angle is equal to sine -1 of 0.3 over 0.34. That's great. Let's get a calculator and actually calculate it. So 0.3 divided by 0.34. That seems like a pretty good way to go about it. Here it is. 15 over 17. Let's do inverse sine of that. Close the brackets. I'm going to get 61.92. 61.92 degrees. They always seem to write at 3 decimal places or 3 sig figs. So let's write another number on that. Let's write it as an 8. There we go. That should be the angle of sloping side. That's it. Let's get the last bit, the surface area of the cone in millimeters. The surface area of the cone in millimeters. That is quite a long question. Let's see what we can do. I'm going to need another picture of my cone. Just copy it and get it all set up. Okay. It's in millimeters this time, so I want to keep everything in millimeters. Be careful about those units. This was 160 millimeters. Now the formula for surface area of a cone is 2 bits. It has the curved surface area around the outside. Curved surface area, which is pi RL or pi RS, where S is the slant height. L is the slant height as well. We can call it slant, or sometimes you'll see it as S. It's the same thing. We can plug in the pi, we know what it is. We know R is equal to 160, and I know L is equal to 340. So that's really good. I'll calculate it in a second. Now I need the base, and the base is a circle, so that's going to be pi r squared. It's quite easy as well. Pi, I know r is 160, 160. Great. That looks like all we need. We just need to plug it into a calculator and make it work. It wasn't that hard. It's just knowing the formula. So 160 times by 340, times that by pi. That's good. And then I guess I could just add 160 times by pi onto the end of it. It equals 171405. 171405. Let's just call it 0.3. You probably don't need that many decimal places or significant figures, but that's it. This is the... Oh, it said excluding the base. I did not see that. So, whoops, I do not need the base on there, so let's delete that. And we do it again, just this bit. I think I can just take... let's just do it again. So, pi times by... Why would you not do the base? That doesn't make any sense. Okay. Got to read the question really carefully 2 or 3 times. So now it's 170902. 170902 millimeters squared. Just check it. Oh, that actually round up to be a 3. But that's it. Looking good. Right, next question. Okay, let's look at the next one. Number 4, a function is given by this equation. Determine a table of data for the range and show a method and then sketch a graph. Okay, we're going to determine a range of data. Basically, you can graph any function by plugging values into it. So that's exactly what we're going to do. Let's make a table of values. Here's x and here's y. And I'm going to... This has to go from -2, -1, 0, 1, and 2. But I'm not going to start at -2 because I think it's really hard to calculate. I'm going to start at 0 because it's going to be a lot easier. I have to plug them in. So I'm literally going to do 0 squared times by 2.5. So I could write it like this if you want to see it. What I'm doing, it's really easy because 0 times 0 is 0 times 2.5 is 0 plus 1 is just 1. So this is actually a set of coordinates. This guy and this guy is a set of coordinates. I'm going to do that for each one of them. 2.5 times by 1 squared plus 1. 1 squared is just 1 times 2.5 is 2.5 plus 1 is 3.5. And then next one is a bit harder. 2.5 squared. I can do on a calculator, of course. That's going to be a 4. Look, I'll prove it to you. Let's grab this. So we're going to have, 2 squared times by 2.5, which will make a 10 plus 1 is 11. So this is going to be 11. -1. Now -1, when you square it, is the same as +1. So it's actually going to be exactly the same as this. It's going to be 3.5. But again, I can prove it to you by doing 2.5 times by -1 using a special negative button. If you use the other negative button, it won't like it. It might like it on a Casio. Let's try. Yeah, it's good. It doesn't have any problem. But other calculators, they don't like it. Casio is really good. Square that thing, and then we're going to add 1 onto it. That gives us 3.5, the same as the other one. So 3.5, and then plug in 2, -2. That will give us the same as 11. In fact, I could have just done this to start with. We can just delete that, put a 2 in there. We get 11. 2.5 negative 2 squared plus 1 is equal to 11. So now we've got all these values, which is great. These are actually coordinates, like I said before. So it says sketch a graph. I probably should sketch it quite well. It needs to go up to 11. So I'm just going to go grab a bit of graph paper. Let me just grab that 1 second. It has to go up to 11, right? So it can go, it doesn't have to go down very far. Oop, wrong button. It has to go left and right a little bit, okay. So I grabbed some graph paper, here it is. Oh, that's nice, it's all being labeled up for me. So let's see. This bit is already done, that's part A. Part B is actually sketching a graph. Yeah, it's easy, but you know, just make sure you draw the lines correctly, put equal spacing and stuff, don't mess it up. Then these are how we're going to read the coordinates. Negative 2, 11. So negative 2, 11. Then negative 1, 3.5. I can't do 0.5s on my graph. You see, that's a terrible thing. I should have included half values on here as well. I didn't. Oh no, what can I do? 0.5, I should redraw the graph. I'm not going to, I'm just going to write it there. Okay, and then 0, 1 right here, and then 3.5, so sorry, 1 and 3.5, 1 and 3.5, that would be right here, and then 2 and 11, so 2 and 11, it's right here, and it did say sketch it, so I better draw a line through it. This is pretty hard on computer. It's going to be not so hard in real life. Ugh. Let's try one more time. It has to be one solid line. You can't do sketch lines. So, I mean, you just draw it and then erase it afterwards. That will do. It's not perfect. I suppose I could draw it a bit better, but whatever. The reason why I want to draw it quite well is from your graph, estimate the answer for x when y is equal to 5. So this was part B. Now part C is y is equal to 5. So let's zoom in a bit on this because y is equal to 5. This is the y-axis. This is y is equal to 5. And it's actually going to have two solutions because it's going to be here and here. It's going to go from here to either side. If it only had one side, I wouldn't bother doing it on two sides. But it goes down to here, and it goes all the way down here. So this is even worse because I can't see what numbers they are. So I should have drawn my graph a little bit bigger. This is 1.1. This is 1. This is 2. So what do you think? 1.2? 1.2. And this is negative 1, this is negative 2, so I think this is negative 1.2. It does say I should do it from the graph. So I did do it from the graph, but we made an estimate. But we can always check it. Let's plug it in. So I'm saying C is equal to, C is x is equal to 1.2 and x is equal to negative 1.2. The two values, there's two solutions for it. Let's just check it. What happens if I put 1.2 in here? It doesn't matter if it's negative or positive. Let's give it a go. How close is it? 4.6. It's pretty close to 5. I don't think that's that bad. If I put in 1.3, and it's a little bit too big, so it's like 1.25. Yeah, it's getting closer. It's better, but I think this is okay because I meant to do it from my graph. So if I'm doing it on a calculator, I'm kind of like lying. So that's it. We got 4 part C done. Okay, let's do question number 5. This one looks a bit longer. It's going to take a bit longer to go through it, I think. A mass of 100 kilograms has a velocity of 2.5 meters per second. Is it moving on a flat surface? Well, it doesn't say how it's moving, but let me draw it because I want to try to convert it into picture format because otherwise it's a lot of information. So it has 100 kg and it's moving at a velocity of equal to 2.5. Well, its velocity is uniformly increased to this much. So actually the velocity, the starting velocity is u, it's 2.5. The final velocity is v, that's 3.5. It looks like I'm going to do a Suvat equation on this, but I think I have to do an F equals ma to start with because calculate the accelerating force, we're going to start with F equals ma. We got some more information. We got time is equal to, yeah, it's definitely a suvat. Look at that. 15 seconds, yeah. Friction can be ignored. Well, that's good. Makes life a lot easier. So let's have a look at the accelerating force required. Yeah, we're going to need F is equal to ma. Force times mass. Force is equal to mass times acceleration. Because we have the mass, we need the acceleration. I need the acceleration. 4 marks. I need the accelerating force. So in order to do that, I need to get the A. So I need to get the acceleration of this object. I got it here. It's a suvat equation. So how we're going to do suvat is write down SUVAT. And how suvat works is, well, I need to go get the formulas because I don't remember them. So that's really annoying, but I have to go get them. I don't know the distance traveled, but I don't care about the distance traveled. I do know the U, I've got them here. 2.5, I know the V, it's 3.5. I don't know A, I want to calculate, so let's call it X, so I know what I'm looking at. And T is 15. Now I have to go get a suvat equation. So I'll just do that, 1 sec. Just go get it. Alright. Here's some suvat equations. And really to get through this test, you only need 2 of these, occasionally 3. Right? You only really need 2 of these really well. So it looks like there's a lot, but you're always doing the same thing. So how this works is we're looking for A, we don't have any S. So anything that involves S, I'm just going to cross out. So this one doesn't have an S, this one has an S, this one has an S, this one has an S, this one doesn't have an S. So I'm going to use this. I'm going to use velocity final is equal to initial plus acceleration times by time. Great. Guess I can delete this now. Don't need that anymore. We're going to calculate this. We got to plug in the values. We got 3.5. Let's grab a different color. This is going to be 3.5 is equal to U, which is 2.5 plus A times by 15. Now we're going to transpose and solve for A. So that involves minusing 2.5 from both sides. So minus 2.5 from both sides. What's 3.5 minus 2.5 is just equal to 1. That's now 15A. I minused it. 3.5 minus 2.5 is equal to 1. Then I simplified this a little bit. Now I want to divide both sides by 15. So it looks like this. So now I've got my A value. I know the acceleration is equal to 1 over 15, which I can write as a decimal if you like, but it doesn't really need it. It can just stay like that. 0.666. The reason why it can stay like that is because this is kind of ugly. This is meters per second squared. I'm still going to write as a decimal because you guys are engineers, and well, that's like not a really good way to have it if you're an engineer, I guess. 0.6667 is better. So this is equal to 0.066667 meters per second squared. This is the acceleration, but it's not the force. We have to go back to F equals ma to get that. So the final part of the question is calculating accelerating force required. So F is equal to 100 kilograms times by that 0.066667, which luckily is still my calculator. I can just times it by 100. It's going to be force is equal to 6.667. Let's give it one more 6, they're recurring. And because we talk about kilograms, seconds, this will be in newtons. So I could just write N for newtons. Really, that's it. That's part A done. Now we got to do part B. So let's make some more space because, well, there just ain't enough space, is there? Right, so maybe the picture is going to change a little bit now. Let's see, let's set it up. Here it is. This will be part B. Right, so a brake is applied and the velocity of the mass is now retarded, uniformly retarded at 0.5 meters per second. So actually I know the acceleration is equal to negative 0.5. It's being slowed down from the initial velocity. So I want to write down suvat again. Let me just write down suvat because there's a lot of suvat information here. So we got SUVAT, and the initial velocity, which is U, that was equal to 3.5 meters per second, and then it comes to a rest, which means it stops. So the final velocity is going to be equal to 0. And looks like we have to calculate the time taken and the distance traveled. That is the time taken, and that's the distance traveled. So it's a really common question. These always come up like this. So for now, I'm going to go grab my Suvat equations because I don't remember them and I need to memorize them. Well, we only need to memorize 2 of them for the quiz. So, okay. Again, which one should we find first? The time taken. So if I'm trying to find time, I don't care about the distance, which is displacement, which is s. So anything that has an s, I can just cross out. Well, that's the same one we had last time. So this is I. We can say the final velocity is equal to the initial velocity plus acceleration times by time. So that's a 0 is equal to 3.5 plus negative 0.5 because the acceleration is negative because it says retardation, so it means it's slowing down, so it has to be negative, times by time. And that's exactly what we're trying to calculate. We can transpose and solve for this. Clean it up a little bit. Whoops, 0 is equal to 3.5 minus 0.5 t. Let's add that to the other side to pop it over. So now it looks like 0.5 t is equal to 3.5. Divide by 0.5 on both sides, or divide by 2. I meant dividing by a half is the same as timesing by 2. That's what I'm trying to say. So now we've got t is equal to, do this on a calculator just to be sure. What's 3.5 divided by 0.5? It's equal to 7. So 7 seconds, because we're talking about time, right? Just kind of checking that through in my head as I'm saying it. Yeah, it's time. It seems to make sense. It's not amazing amounts of time. It's just right. Okay, so part 2, II, is the distance traveled. So I'm going to go back to my Suvats, and this time I do have a t now, but do I really trust it? I don't need to. I can do anything involving just s by itself, no t's. So if it has a t, I'll cross it out. Oh yeah, I'm going to use this one right here. V squared is equal to u squared plus 2as. Let's give that a go because I know what v squared is. It's 0. U squared is 3.5 squared plus 2 times by a, which is negative 0.5, times by s, which is what we're trying to find. Should have called it x because it looks too much like a 5. But okay, we'll keep it like that. 0 squared is 0. 3.5 squared, I don't know, what's that? 3.5 squared is 12.25. 12.25. 2 times a negative 0.5 is negative 1 for sure. But let's do it on a calculator just to check. Just so you can see it. It's definitely negative 1, so negative s. Which means s must be equal to this, if it's 12.25. But let's add s to the other side. So we got s is equal to 12.25 meters. And that's the final answer. Let's go read it to make sure the distance traveled. Is for the retardation period, not the total period. So yeah, that's it. We got the time is 7 seconds and the distance is 12.25. That's really good. Okay, now let's look at question number 6. A generator flywheel has a diameter of this much and rotates that fast. Let's draw a flywheel. I mean, a flywheel is going to be a circle, right? And it has a diameter of 0.85. 0.85 meters. And it rotates at 9,500 radians per minute. That's a weird measurement. Why do you measure things in rads per min? But okay. I guess it's to get it into revolutions per minute. Calculate each of the following. The linear velocity at a point on the rim. The linear velocity is if you had an object on the circle like that, on the wheel, on the flywheel, as it's spinning around. I think I can spin it around. So as this thing is spinning around, and imagine it flew off and hit you like this, and then suddenly the wheel stopped spinning, and this thing was like, whoosh, and it hit you in the face. And it's the velocity, it's the speed at which this thing would hit you in the face. Right, so if we can calculate the speed that it's going when the flywheel stops and this thing starts flying off, that will be the linear velocity. It's the equivalent of a straight line speed. Okay, we can do that. Let's try to give it a go. I think we're going to have to calculate the distance it's traveling because we know that velocity is like speed. Velocity is like basically speed in this case. And it's going to be the distance divided by time. So I want to see how fast this thing is traveling, or how much distance it's covering and how long it's taking to do that. So the distance it's traveling is going around the edge of a circle. It's going around like this, right? So it's that's the circumference of a circle divided by the time taken. Now you need to know the formula for circumference of a circle. Luckily, it's really easy. It's pi d. You can use 2 pi r as well, but I don't like that because it looks so similar. This is circumference, which is the distance around the outside, right? I don't like using this one because it looks so similar to the area. Area is pi r squared, and there's too many 2's and too many r's. It looks too similar, so I just like to use pi d. We're going to divide it by time as well. Pi d is, well, that's going to be pi times by 0.85. And the time taken, oh, we need it in meters per second. I'm just checking I got everything right. Yeah, we need it in meters per second. So this is going to be in meters. Yeah, it's going to be in meters. That still stays the same. How many seconds? We're doing this. What? How does? Oh, wait a second. Wait a second. I need to do a bit more work on this. Yeah, this is true. The distance traveled, but it's not just doing that amount of distance. It's doing the circumference, which is pi d, which in this case is 0.85 pi meters. This is meters. I can calculate that just to give you a better idea what we're talking about. Let's times it by pi. It's about 2.67 meters, but it does that. I don't know how many times it does it in radians per minute. So we're going to turn that into radians. 1 second. I want to turn this into how many revolutions this thing is doing, because 9,500 radians. How many radians are there in one revolution? Well, let's do it the other way. I want to turn it into revs, into revolutions. So 1 revolution is actually going to be 2 pi radians. How do I write this? Where can I write it? 1 revolution is equal to 2 pi radians. If you haven't seen radians, we need to talk about it. We'll go over it in another video. But basically, there's about 6 because 2 pi, 3.14 times by 2. This is how many radians there are. There's about 6.28 radians in a full circle. So if I divide my 9,000 by this, it tells me how many revolutions we've done. So I can say 9,500 divided by 2 pi. And it'll tell me there's 1,511.97 revolutions. So 1511.97 revolutions in a minute. So let's just talk about the revolutions first of all. If it travels 2.67 meters for 1 revolution, that's the distance to go all around the outside. Now it's going to do that 1,500 times. Then I can calculate how many meters it's traveled. 1511.97. So let's take that number I had before and just times it by 0.85 pi. This will be more accurate. I don't want to make any rounding errors, so I'm using exact values. So it tells me that it's traveling 37.5 meters in that 1,500 revolutions. To spin, it spins around a whole bunch of times basically, and that blue dot is going to cover 4 kilometers. Look at that, 4,000 meters in a minute. Well, that's pretty fast. I mean, okay, so then we got to do it. What is it, meters per second? So the distance is going to be 4,037.5 meters, and I want to do that. This is per minute, so that's in 60 seconds. 60 seconds. So how do I do it into 1 second? Well, I just divide it by 60. So I can actually just calculate this as it is. Take this number, divide it by 60, and it'll give me the answer of 67.29. 67.29. 29166 meters per second. So it's the linear velocity is this much. That's how fast it would be traveling if the thing flew off and hit you in the face. That was part A. Now we're going to do part B, which is the rotational speed of the flywheel. I think it's going to be a lot easier. Let's make some space. Drop it down over here. Rotational speed. I still need my picture. Let me just go grab my guy. Here he is. It's got all the information on it. Let's drop it down over here. Alright, so let's see. The rotational speed in revs per min. Well, we just worked out revolutions per minute, in fact. We worked it out as being this many revolutions, and that was per minute. So that's actually the answer on this one. Wow, that's easy. So B is 1511.97 revs per minute. We already had it. That is the end of that. And now C is the number of radians turned when the flywheel rotates through 150 degrees. That's a very easy question. We just need to know one thing. We know degree and we know radian. Now I need to remember one piece of information in order to do this. There's in 360 degrees, there's 2 pi radians. So I can work it out for 150, no problem. There's a couple of ways we can do it. I can divide by 2 pi. That would give me, I'm gonna do it like this. I'm gonna turn it into, how do I turn it into 150? Is I'm going to, there's lots of different ways you can do it. I can use a formula, but I'm gonna turn it into, I guess, 1 degree. That would be 2 pi divided by 360. I literally just divided this by 360 and then divided this by 360. And then I'm going to times both sides by 150. It's kind of a long way to do it, but it's easy to do on a calculator. So easy. So why not? Just make that a bit longer. Like that I can convert into anything. I just did like I basically just made a formula. So this will be 150. And then, well, let's see what this is going to be. 2 pi divided by 360 times by 150. Pressing equals every single time. 2.6178. 2.618. 2.61799 radians, basically. That's the answer. That's it. 150 degrees. There's, like I said, there's a couple of different ways we can calculate it. I'm sure we'll do the question again at a later date and we'll do it a different way. This is rads, but pretty simple. Nice. All right, next one. Okay, so now we're going to do question number 8. There is no question number 7 because on these past papers because they've changed some of the material in 2018 and removed some of the questions. So we will still cover all the topics, don't worry, but we're just going through his past papers, which these are now no longer relevant. Question number 7 is no longer relevant. It's actually in GES1. Okay, great. So a box with a mass of 40 kilograms rests on a horizontal surface. Let's draw that, because it's a lot, otherwise it's too much information for me to take in. So here's a box, it's 40 kilograms and it's resting on a horizontal surface. That's good. The box has a force of 150 newtons applied to it, so at an angle of 20 degrees to the horizontal surface. It doesn't say if the force is being pushed down upon it like this or it's being pushed up. It just says 20 degrees to the horizontal surface. It doesn't say in the question. We're going to have to make an assumption. It depends on how we want to assume it, because it's being applied to it. It could be you're pulling it and it's going 20 degrees up. And this is going to make a little bit of a difference to the amount of friction we feel, except there's no friction. In the second part there is, right? It's going to make a little bit of difference to the friction, because if you're pulling it like this, you're actually lifting the box up a little bit. So the box would feel less friction on the surface that's touching on the box on the bottom here. It would feel less friction because you're lifting it up a bit. And if it was going the other way, then the box would feel more friction because you're actually pushing it down into the ground. So then there'll be more friction going on here. So we've got to make a decision about which one's right, because it doesn't say in the question applied at 20 degrees to the horizontal surface. What do we say? We just assume it's like this then. Let's assume we're pulling it upwards, because, well, I might be if I was pulling a box like that. Again, I might be pushing it from behind and it would not be helping. If I was a guy pulling it like this, then I guess I might be pulling it at a slight angle upwards, and that might help things a little bit, actually make it easy to pull. So we're going to go for that. But like I said, we've got to make a decision somewhere. So, all right, let's just lock that down. Then we're going to say this is 20 degrees then here. This creates a force triangle. Let's just see, we've got 150 newtons. And this thing is 20 degrees. Okay. Find the acceleration of the box with no friction. We actually have to break this down into its horizontal components and its vertical components. We're pulling at an angle, and some of that is going to be translated into horizontal, some of it will be translated into vertical. And we're going to use a bit of trigonometry to do that. A bit of SOHCAHTOA, I think, on the angle. Yeah. So let's do that right now. Let's draw it over here. We've got a bit more space. So we've got this triangle. The thing is 20 degrees on this angle here, and then we've got 150 newtons on this angle, on this hypotenuse pulling it in this direction, which is absolutely fine. We can just equate the size of the sides with the actual force felt. So if this is 150 newtons, we can use SOHCAHTOA. I'm going to draw a little guy so I can get some reference. This is the opposite. This is the adjacent to him. And then this is the hypotenuse. Now I'm going to use that to write down silly old Harry caught a lot of haddock trawling off Africa. And then I'm trying to calculate the opposite and the adjacent really. For this first part I need the adjacent, but then for the second part I need the opposite anyway. So I might as well do both of them right now. Let's calculate the adjacent. I've got the hypotenuse and I want the adjacent. Hypotenuse and adjacent. Adjacent hypotenuse, that's going to be cosine. So we can write this down as being cosine of the angle is equal to the adjacent over hypotenuse. We can just plug the values in. So we can say cosine of x, no, cosine of 20, because it's 20 degrees, is equal to the adjacent. Let's call that guy x, and we'll call the opposite y, because it's going in the y direction, it's going in the x direction. So the adjacent x over hypotenuse, which is 150. Really easy to solve. We just multiply both sides by 150, so we get 150 cosine of 20 is equal to x. This will be the horizontal force. Let me just grab my calculator, plug this stuff in. So we're going to type in 150 cosine 20. 150 cosine 20 is 140.95. 140.95 newtons in the horizontal direction. I suppose we better label that horizontal. It'd be nice if we could actually know what we're talking about. So this will be the horizontal force. Let's call it horizontal force. Now we could do the vertical force while we're here, because like I said, we're gonna need it in the next part of the question anyway. So we might as well calculate it right now while we're still doing this stuff. So let's do the vertical force. All right. And that's gonna be, well, we've got the hypotenuse and we want the opposite this time. So we want h and o, that's gonna be the sine. So we can write this down as being sine of the angle is equal to, let's see, the opposite, it should be looking up here, opposite over the hypotenuse. And we know all that stuff, so we just plug in the values. Sine of 20 is equal to the opposite, which is y over 150. It's a really easy equation. It's basically the same thing. We just swap out. Now we're going to have 150 sine 20 is equal to y. We're just swapping out the cosine with sine. So plug that into a calculator. So it's actually exactly the same. I can literally just delete this and plug in sine. 100 like this will be good. I get 51.3. So y is equal to 51.3, just down there at the bottom. Oh, let's make it look like a point. This is newtons. Great. So we've got quite a lot of stuff going on there. Looks like we're going to have to make some more space. Let me just grab my force triangle and drag him over here so you can see things a bit clearer. And then we'll fill in these sides. Let's call them what they should be now. We said that this was 140 on the x-axis. So this will be 140 newtons on the x-axis. That's pulling it in the x direction. And it's 51 in the y-axis. Whoops. Let's just grab that and drop it up here. Clean it up a bit. Oh, I better get my box as well. I'll put it back on my box because we had this box over here. Let's drag all this over to the sides. We got more space. Don't need the guy anymore, really. Get rid of this. All right. So this is what we're looking at. We're looking at something that's pulling it to the right. Let me get in the center. Sorry about that. Pulling it to the right with 140. Let's grab that. 140 newtons going to the right there. Which, this is what we care about. Let's go back and get the question as well. So here's the question. I think we're ready to go on that now. Yeah. So we got the horizontal force and the vertical force. Of course, the vertical force is pulling it upwards because we made that decision earlier. It might be pulling it downwards. It could be pulling or pushing it downwards, but we're going to have to decide because it doesn't say in the question. The acceleration of the box with no friction. Anytime it says acceleration, we're going to be using F is equal to ma, I think, because we've got the mass of the box, we want to calculate the acceleration, and we know the force applied in the horizontal direction, which is 140. So F is equal to 140.95. The mass is equal to 40 kg, just 40 I suppose, kg. And then, yeah, we don't need units because it's all in kilograms and newtons, it's all good. And then what is the acceleration? That's what we're calculating. So we can go ahead and plug this in as 140.95 is equal to the mass, which is 40 times by A. That's pretty easy to solve. We can just divide both sides by 40. That'll end up with 140.95 divided by 40 is equal to the acceleration. Let's have a look at that. 140.95 divided by 40 is equal to 3.52375. 3.52375. And because it's acceleration, it'll be meters per second squared. So we got the acceleration of the box with no friction. That's part A. Done. The acceleration of the box when the coefficient of friction is 0.35 exists between the box and the surface. So let's do the second part. Okay, gonna need some more space, so let's drag it off to the side. Drop that down. I'm gonna need my picture again, so it's a really good thing that we made that vertical part, because this is gonna be really important now. So we're pulling on this box, and like I said, we're pulling it up a bit. We've got to have a look at how much we're pulling it up, because it's really important for the friction equation. Friction, the equation for friction, I think friction is fun. Friction is fun. That's it. Friction force is equal to the coefficient of friction times by the normal force. The normal force is going straight up. So normally that's just going to be gravity times by the mass, which is like 9.81 times by the 40 kilograms to turn it into a Newton. We need to do that straight away. Oh, and they actually told us. That's not exactly true. I'm so sorry. Because we are counteracting gravity a little bit with this 51.3. So we've got to do a bit more work here. Let's see if we can have a look at just that box, what's going on with it. The horizontal force we don't care about anymore. All we care about is what's going on with this box vertically. So there's gravity pulling it down, which would be 9.81 times by 40. This will create a downwards force, which is going to stick it to the ground. So let's find out. Let's do 40 times by 9.81. That gives us 392.4 newtons, pushing it downwards. But then we said we're going to be pulling it upwards with this force of 51.3 newtons, which we calculated earlier. We got it from these calculations earlier here. So that's really good, because we're going to be doing that pretty much every single time anyway. We're going to be doing horizontal and vertical. Okay, so now we've got this vertical force pulling it upwards. That's going to counteract this downwards force, and it's going to not stick it so much to the ground. So let's work out what the net force or the overall force would be vertically. It'll be 392.4 minus the 51.3. I'm just going to scoot that up a bit so we've got a bit more space. Then I'm going to grab my calculator and let's calculate it. So we've got this guy minus a 51.3. That gives us 341.1. 341.1. Well, that's how much force is now pushing this thing downwards. Even though we're lifting it up a little bit, it's still pushing down quite a lot. This is the overall resultant force, the net force vertically, pushing it down. That's also what's going to stick it to the ground, right? So we can use our fun equation now to solve for this. So we can say the force is equal to the friction, which is the coefficient of friction, sorry, the 0.35 times by this vertical force pushing it down, the 341.1. Let's calculate that. Let's see, this guy times by 0.35. 119, it's going to be 119.385. 385. This is the friction force. Okay, the acceleration of the box when the friction coefficient exists between the box and the surface. We're not done yet. This is just the friction force that's resisting the motion. And now we have to go back and look at the horizontal motion. So let's draw another picture of this. Can I grab my box again? Let's drag it over here. I guess I should bring the question with us. Let's go get that as well. Alright, so we got this again, another setup. We don't care about the vertical anymore, so I can basically get rid of all this. All I care about now is that we are pulling it forwards with 140 newtons, but there's a resistance on this, which is caused by the friction of 119 newtons, 119.385. Let's grab that and we put it in here. So this is what's pushing us back again. It's resisting the motion because that's what friction does, isn't it? It resists the way you're pushing the thing. So the net force, the net horizontal force, you know, like the force that we're actually pushing this thing forwards with was going to be 140.95 minus the 119.385. So let's find out what that is. 140.95 minus the answer from the last time. We get 21.565. 21.565. This is actually the resultant force, is what's left over. We can call it resultant force. Resultant horizontal force, I suppose, because we're pushing it this far. This much force is left over after we overcome the friction. It's like friction's a bit like tax. You got to pay it, and then whatever's left over, well, we've got this much left over. That's actually going to be useful. So we can write again. We're going to do an F is equal to ma to find our acceleration from the amount of force. The horizontal force that's resultant after all this is going to be that 21.565. Now this is equal to the mass of the object, which is 40 kilograms, times by A. We can transpose by dividing by 40. So we get 21.565 divided by 40. This will be equal to our acceleration. So I've still got it on my calculator, doing pretty good. I haven't messed it up so far. Divide by 40. I'm writing down all these numbers in case I do mess it up. But it looks pretty good. We got the acceleration as 5391, 0.5391, 125. All right, so the acceleration is equal to 0.5391. I guess I don't need so many decimal places, but I might as well put them on. Meters per second squared. That looks like the acceleration after we apply the friction to it. All right, really good. That was question 8. Let's do question 9. Okay, this is question 9. A pump impeller is uniformly accelerated from this many revolutions to that many revolutions in 10 seconds. Find the angular acceleration in rads per second squared. Radians, seconds squared, revolutions in minutes. Ugh, what a mess. So we're talking about a pump impeller. Basically, we're talking about something that's spinning. I mean, I'm sure it's like a propeller, a spinny thing, but we're talking about a spinning object, right? I should really get a picture of that and prepare it beforehand, shouldn't I? But let's have a look. This thing is going to be 500 revolutions per minute. We can say it starts at 500 revolutions per minute. I could actually put 1 minute like this, 1 minute. And then it's going to end at 700 revolutions in 1 minute. And we got to calculate this stuff in acceleration in radians per second squared. It'd be nice to get it into those kind of units to start with. So how many revolutions, how many radians in one revolution? We saw this earlier in another question. That is gonna be one. Let's write it like revolution up here, and then our radians up here as well. So one revolution is a full circle. You remember how many radians there are in one circle? It's 2 pi radians, which is like 6 or something. Right. Okay, that's pretty good. So if you want to turn revolutions into radians, we just literally multiply by 2 pi. So I can multiply this by 2 pi to turn it into radians. So it's actually going to be 1000 pi, but let's do it. 500 times by 2 pi. Oh, you can't see the calculation. There it is. It's going to be 1000 pi. I can just leave it in terms of pi, or I can write it as this number. Let's write it as a number. You guys are engineers, so you like numbers. So 31, 41, 59. 31, 41, 59. That's how many revolutions is going to be. No, radians is how many radians is going to be. Let's see. Let me just move this across, get a bit more space. So this is going to be radians. And then, well, 1 minute is all very good, but I want to turn it into seconds because we're trying to calculate stuff in seconds. So that's pretty easy. I can turn that into 60 seconds. Then I want to turn it into just in 1 second. Let's have a go at that. If I want to turn it into 1 second, it means I would have to divide everything by 60. I literally just do this on a calculator, but the reason why this is because we're simplifying a fraction. Divided by 60 to get 1 second on the bottom. 60 divided by 60 is 1. But like I said, it doesn't really matter. We don't need to write that out too much. I mean, I'll do it anyway. Okay, let's divide this by 60. This might not be the best way to do it. There might be a cleaner way to do it, but we'll cover it in future videos. I'm going to do it this way right now because it's working, and then I might do it another way later on. So sometimes you got to see stuff in multiple different ways for it to make sense. 52 point, well, you do have to see it multiple different ways for it to make sense for sure. 52.3598. Let's see. 5235. 5235. 9877. 9877. All right, cool. That looks good. Now that's in 1 second. Now we can do the same thing here. We can do exactly the same treatment. We can times it by 2 pi. Turn it into 700 times by 2 pi, and that will turn it into 4398. There's a lot of numbers here, so there's a different way I can do this to avoid having all these numbers, but I'm just going to do it this way for now. 4398. 4398. The other thing is, we don't have to be so accurate when training, but we do have to be accurate in the exam. So I could put less numbers on here just for ease. Okay, so it's also in 60 seconds. We're going to do the same treatment. We're going to divide it by 60. So let's get that number divided by 60. Here we go, 73.3. 73.3 over 1. That's how many radians per second we're doing. So let me write this down as rads per second. And this is rads per second. Right, okay. Now we got to talk about unit. Let me zoom out a bit so you can hope you can see it all. Can still see that? Looks all right, doesn't it? Okay, so we got this, yeah, in 10 seconds. Oh, in 10 seconds. Okay, so that's actually going to be a suvet. There's cut down versions of this, but then you have to remember more formulas. So I'm going to keep using suvet again and again. We can just do a suvet equation. Like I said, there's a lot of different ways to do this. Let's look at suvet. Because we have 3 bits of information. We have initial velocity, which is like 52.3. Let's just round it up to 6. I know it's not brilliant. I'm going to try and keep it as numbers when I type it in the calculator, but for writing it down, I want to unclutter this a little bit. 73.30 on the final velocity, that's what it was, right? Yeah. And then we got the acceleration, which is what we're trying to calculate. Let's call it x, so I know what I'm looking for. And then we look for t, which is time, which is 10 seconds. Oh yeah, I totally forgot. This is angular acceleration and it says angular velocities. It really doesn't matter. It's still suvet. When you see this in school or you see it in class, they're going to use different symbols, but we don't need to. We can just use these same symbols we've always been using for linear. It's the same for angular. Technically, it's not correct because these we should be using different notation because it's not the same as initial velocity, but actually it doesn't matter. It's equivalent anyway, so we can just use this. It's fine, and it saves you having to learn like 2 sets of equations, which is so confusing. Okay, we want to use a suvet, so let me go grab my suvet I had earlier. Where has he gone? Up here. All right, again, like I said, we don't need all these suvet equations. We just need really 2 of them to get through this exam. So we're looking for A, we don't want S. Anything with S in it can go. So you can see it's the same equation as last time. It's going to be V is equal to U plus AT. This is going to be 73.3 is equal to 52.36 plus acceleration, which is what we're looking for, times by time, which is 10. All right, let's minus that from both sides. We minus the 52, so 73.3 minus 52.36, 73.3, I already had it in my calculator, didn't I? Divided by minus 52.36. All right, that's 20.94. 20.94 is equal to 10a. Divide by 10. We're going to get 2.094 is equal to a. This is in rads per second squared. So I guess we should say that. Rad per second squared. That's it. We didn't have to use different formulas. It was absolutely fine. We got the right answer. Nice. All right, let's do part B. The number of revolutions turned during the acceleration period. Number of revolutions. Every time we do suvat, we end up calculating for two different values. We just calculate for acceleration. Now, technically, the number of revolutions will be the distance traveled. The number of times it's going to go round in a circle, well, that will be like a distance traveled. So we can do the same thing. We're going to use the same suvat to solve for S this time. And seeing as we got A now, well, we can use it to help us. Let's just drag this over to the side so we've got some space to work in. And now we're going to do part B. Let's see if that looks okay. Yeah, it looks all right. This is going to be part B. So we're still spinning an object around. We're looking for the S this time. Oh, I need my suvat, don't I? Yes. Number of revolutions. So I don't want this to be in radians anymore. This radian thing is no good to me. I want us to have, let's have a look at the initial velocity that was equal to 500 revolutions in 1 minute. Or we could say in 60 seconds, right? I could write 1 min, and this is rev. And then I want to be talking revolutions anyway, so this is good for me. But I want it in 10 seconds. So let's put it into 60, and then I'm going to do it in individual seconds. The standard units should be seconds, meters, kilograms, newtons, so not minutes. Let's change this. So I can simplify that by dividing by 60. So let's do 500 divided by 60. It gives me 8.33333. That's fine. I can deal with that. I can put a bunch of 3's into my calculator. This is number of revolutions per second. That's the initial. And then we're going to have the same thing. For the final speed, or the final velocity, is going to be 700 revolutions in 1 minute. So same thing, but let's put 700 over 60 and then put it in the calculator. 700 divided by 60, we're going to get 11.666. So 11.666, I can do with that. This is revolutions per second. Then we're going to plug it into one of these in order to find what we're looking for. Let's just scoot this across. All right. So what are we looking for? We're looking for S. We don't want to use the A because we might have made a mistake and that would carry through. So anything with A in it would be good to get rid of. We can use it. Looks like we're going to be using this. Because we talk about revolutions in seconds, this should be fine. The distance traveled, or the number of revolutions turned, will be the initial value. So it will be V plus U over 2 times by T. It's a mini average. Basically, it's going to be speed times by time is equal to distance. So S is equal to 11.66666, etc. plus 8.33333, etc. divided by 2 times by 10. Let's do that. I got my 8.666. It looks like an 11.6, right? But that's recurring. You can see if I keep pressing this button, it flips between the fractions and decimals. This button is really useful. Then we can do 8.3333333. That would be great. Oh, look, it made it a nice number. 20 divided by 2 is 10 times by 10 is 100. So it's going to do 100 revolutions. So we can say the answer is 100 revolutions in that acceleration period. 4 marks. It's good. Let's do next question. Okay, now we're going to do question number 11. A pneumatic actuator has a rod of 0.6 meters long. Okay, that's enough information for me. Let's draw a picture of what that means. Pneumatic actuator, so that's like the thing inside of like a JCB digger, like this thing that sticks out the end like this, I think. It's a piston, right? It's going to go in and out. And it has a rod that's 0.6 meters long. So let's just say this bit is 0.6 meters. is solid steel, but it can only handle so much, and then it'll break, and that's what we're going to be calculating, basically, the stress and the strain, and how stretchy the steel is. That's a modulus elasticity. It's going to be a little bit stretchy. Okay, so 0.6 meters long with a rod diameter, the diameter of this thing. I suppose I should maybe change it into just a steel rod like this. That's meant to be like a cylinder, I suppose. Yeah, let's draw it as a cylinder because that was a little bit misleading. Let's make it a cylinder. We'll make that thing the proper length, and the diameter is, what is it? Is 15 millimeters. Well, that's a problem because this one's in millimeters, this one's in meters. But okay, we'll fix that in a second. Okay, so it's subjected to an axial pull and it extends by this much. This pull and extension, that's for the strain. Let's do the stress first of all. So let's write down our formulas. What is stress? Oh, what is stress? I think stress is the same as pressure, is how I remember it. So pressure is force over an area, which is, this will be a cross-sectional area, and the force applied is whatever we're picking up. And it tells us, it says we're subjected to an axial pull. It doesn't matter if we're pulling it or squashing it. Either the rod will stretch or the rod will be crushed. And it's the same thing. It should be the same calculation. That's weird, isn't it? So the force in this case, we can say the F is equal to 13 kilonewtons. We can do things in kilonewtons, or we could do things in newtons. We'll have to decide which we're going to choose. As we're working with very large equipment, very large machinery, we'll probably do most of the things in kilonewtons because it saves on all the zeros. Now we've got to get the cross-sectional area of this thing. Because it's a cylinder, it's a rod diameter. I'm going to assume it's a cylinder, and we're going to say the area is pi r squared because it's a circle on the cross-sectional area. We have the diameter, but we do not have the radius. Now, all of our calculations should really be done in meters, in standard units, which is meters, newtons, and kilograms. So this needs to be converted into meters. So I can't think straight, so I'm going to do 15 divided by 1,000. I know that's how you convert it, and it should pop it into meters for me. There we go, 0.15 meters, very nice. I didn't want to make a mistake on these zeros, so I did it on a calculator. Divide by 2 because I want the radius. It's giving me some weird number. I know that's going to be 3 zeros. It's going to be 0.0075 meters, but I can just use it like this, I think. So this is the radius. You can see it's half of the 15 makes 7.5 basically. This doesn't mean meters across. It's really small in meters, which is good. It's fine. Still strong. It'll be fine. Then we're going to plug it into this equation. We're going to get the area is equal to pi r squared. So you can do 0.0075 squared times by pi, which means I just take my answer and square it, and then times it by pi. We get a very small number. Let's use this standard form. This, standard form now. 1.767, or scientific notation. So 1.767. So the area is 1.767 times by 10 to the negative 4 meters. Great. Just squeezed it in there. So now I can compute this. I can calculate the stress on this thing because I got all my ingredients. Let's put it together. Let's say the stress, I guess I want to, let's put it on over here. Stress is equal to the force, which is, we're going to do it in newtons, right? So 13,000 divided by 1.767 times by 10 to the negative 4. My calculator can handle that. That's no problem. I can just do 13,000 divided by the answer because I already had it in there. Now the stress is usually like that. It's massive. 73.56. Stress is equal to 73.56. 49.51, 49.51.47. Why not put that extra few decimals in there? Stress. Now, because we are working in newtons and area, this will be in newtons per meter squared, I think. All right. Just about get all that on there. Nice. That is the first bit done, the stress. Okay, let's move across to the next one, which will be the strain. Let's do part B. Okay, so let's look at strain. We got the same steel rod. Let me just go get it from the last question. We still need the same diagram, but I want to keep things reasonably clear for you guys. I'm sorry for moving around too much. I guess you guys don't get seasick, so it's okay. Right, let's have a look. The direct strain on the rod. So what is strain? Strain is, well, when you're under stress is when you're under pressure. So under strain is actually, I think it's the extension. It's how much you stretch something by. Extension. I don't know if that should be a T, right? I think it should be an S. Extension over original length. Original. So it's how much you stretch something over how much it was originally. That should definitely be an S, right? Extension. I really can't spell to save my life, but it's fine. It's not a spelling test. So the extension over the original. And what is the extension here? It tells us the rod extends by 0.25 millimeters. Again, I want to put this into meters, I suppose, because the original length is in meters. So I want to put everything into standard units. So the extension, yeah, it's definitely an S, my bad, I'm so sorry. Extension is equal to 0.25, again, I'm going to divide it by 1,000. It's going to be some small number, 0.25 divided by 1,000. I got this really small number. I'm going to leave it like that, 2.5 times by 10 to the negative 4 meters. So that's 2.5 times by 10 to the negative 4 meters divided by the original length, which is 0.6 meters. The meters, in fact, are going to cancel. We don't even need to care about the units. But we can divide this. Let me grab it, my calculator, and we're going to do this original number divided by 0.6. Well, I was expecting it to be a bit smaller than that, but we got, yeah, 0.000 416666. This is the strain. That's all it is. Extension over original. We don't need to multiply it by 100. Nope, we just leave it like that. That's great. This doesn't have any units either because the units have cancelled. This is the strain. Okay, now we're going to do part C. That was part B. So let me drop it down there. I'll get my picture still. It seems to be working quite well, so let me grab that. All right. Okay, looking good. Here we go then. Pneumatic actuator, modulus elasticity. So, you know, elasticity is equal to stress over strain. Well, this is really easy because we just did that. So we just plug in the values that we got from the last couple of questions. So let's get the stress. It's over here. Here it is. I can copy and paste that up here. Sorry for moving around so much. And then we can get the strain, which is going to be this number, again from the last question. And we can just pop it in there. And then we can divide it up. And that will do my elasticity, my modulus elasticity. Let's find out. We're doing 7, 3, 5, 6, 4, 9. Hopefully I don't make any typos. I probably will in all of this. It's going to be full of typos. You have to go back and check it, but you can't get like 100% anyway because we're full of typos. That will do. This is the number. This is 1.765. 1.765 times by 10 to the 11. I would round it up, but I suppose I should to 6. That'll do. 11, and the elasticity is in the same units as the stress, as the strain doesn't have any. So this will be newtons per meter squared. This will be the elasticity. This is the modulus elasticity. That's it. Done. Next one. Okay, question number 12. Hope you can see this. I'll zoom in a bit so you guys can see it. It's quite a long question, this. We've got a cylinder with a flat circular base, 20 centimeters, hemispherical top. Piston sweeps 95% of it. Determine the clearance volume as a percentage of swept volume. So the clearance volume is the bit that the piston does not go into. It stays up here, so it'll be this chunk up here. This will be the clearance volume, and then the swept volume will be 95% of that. I can do that right now. It'll be 80 centimeters times by 0.95, because that's how you do a percentage calculation. 0.95 times by 80. It gives me 76 centimeters. So it will sweep up to 76 centimeters, like up here, and then it's gonna stop sweeping. And the question is basically, what is the total volume? No, it's what is the clearance? This is the clearance. That's 76 centimeters over whatever volume this is on top. So let's break it down into a couple of bits. This will be the clearance volume. Yeah. So let's break it down into a couple of bits, because this shape is made from two objects put together. Let's have a look. First of all, we're going to talk about that cylinder. Actually, I can literally calculate the clearance straight away. Let's see if we can break this down so you guys can see it. I don't want to go too quickly on it. This could be, let's say that's the clearance. Let's do it like that. Let's say this is clearance. I suppose I'm going to get a title up here, more to the side. Let's give me the clearance volume, and then and this thing is what, 78 centimeters tall. 78. I already know the radius of this thing, because I need to know the radius. That is going to be 20 centimeters. Let's make it a bit clearer. 20 centimeters, which is really nice. It's really good. Then there's like a little cylinder on top of that, which I just calculated as being 4 centimeters tall. So I can take this cylinder and we can make a little copy of it, shrink it down and squeeze it on top. Let's see if it works. Oh, it did not work. Let's just make another one then. So I'll put it back to where it was. Sorry about that. Let's put another cylinder on top here. Should be exactly the same. Okay, and this is like really thin. It's only 4 centimeters, but the piston doesn't sweep up into this. So this little guy is 4 centimeters tall, and the same radius is going to be exactly the same at 20 centimeters. Then it's got a hemisphere on top. So we can draw a hemisphere on top. Again, it's a really common question. You always get these geometry questions where they're just made from different parts of basic shapes. Again, I didn't have to do it this way. I could have done this as one object and cut it up, but I thought, hey, we already looked at it like this, might as well. This is a hemisphere. So this is going to be, again, 20 centimeters on the radius. And that's all we need for the hemisphere on top, actually. So let's, I don't know, break them into 2 different sections and have a look at each one. Yeah, so I'm going to, how are we going to do? We're going to move that across, and then we're going to look at the swept and the clearance. I said this was clearance. That's not clearance. This one's clearance. That one over there. Get everything organized before we jump into the calculations. There, that'll do. Okay, so let's focus on, this is the swept. Do I need to see it? Sorry, it's been a long day. Making a lot of videos today. All right, this is the last one, so it's all good. So the swept volume, that is just a cylinder. That's pretty easy. Cylinder is going to be base times by height. Volume of a cylinder or any kind of prism is base times by height. The base is a circle, so I can just put in the circle equation, pi r squared times by height. I know radius is 20. I know height is 78. So let's just go for it. We can say this is going to be 20 squared times by 78. And that'll give us a number. So let's go ahead and get that. Pi times by 20 squared times by 78. This is going to be the volume in centimeters cubed of that swept. So it's 98,017.69 centimeters cubed. Wonderful. Now we're going to get the clearance. So same treatment on the clearance, because this little guy here is going to be the same formula as that last bit. So let me pop it up here. We're going to have the volume is equal to base times by height, and then this is equal to pi r squared times by h, exactly the same. It's going to be 20 on the radius, but only have a height of 4 this time. So basically the same thing. I'm just going to delete that and put a 4 in there. That's pi times by 20 squared times by 4 gives me 50, 26. 50, 26.548. 0.548, and then like yeah, that'll do. Centimeters cubed. Now I need the volume of this hemisphere. So we need the volume of a regular sphere. Volume of a sphere is 4/3 pi r cubed. We know r is 20, so it's going to be 4/3 pi 20 cubed. Let's have a look at that. 4 divided by 3. I got to cut it in half. I almost forgot. It's only half a sphere. So I got to cut it in half at the end. Times by pi. Then times by 20 cubed. And then divide that by 2. Because I have to cut it in half. So 16. So I'm going to divide the whole thing by 2 because I only want half a sphere. 16,755. 16,755.16. 0.16 centimeters cubed. So now I've got all my ingredients. I just need to put them all together. I know that the clearance are these two things combined. Is this and this. So let's go get them, put them together. I can add them, right? So clearance is going to be that 16,000 we just worked out plus the 5,000. The 5,026.548. Plug those guys in. 2178. But let's come across here and put it all together. So we're going to say this is going to be swept and then clearance. The clearance volume is going to be equal to this guy. We just calculate 2178. 1.7 centimeters cubed. Then the swept clearance volume as a percent of the swept volume. Swept is this. We've got swept is equal to 98017.69. We don't really need the units. Let's get rid of the units. Because the reason why I set it up this way is because we want to calculate as a percentage, which means we have to divide one by the other. So we're comparing them. 21,000 divided by 98,000 and change. All right. This gives us a decimal, which is very easy to convert into a percentage. You just times it by 100, so you can see it's 22.22222. Times by 100 will turn it into a percentage for us. Times that by 100, we get 22.22%. This is, just check it over, determine the clearance volume as a, yes, as a swept volume. Looks good. It's 22.22%. And that's the end of the test. Thanks very much.